Coming up on this edition of The Climate Show, we're acidifying the oceans. Well, not deliberately, but we do have Professor Keith Hunter from Otago University. He's an expert in this whole entire area, and he's going to tell us what ocean acidification is and what's happening with the oceans and into the future as well. Gareth, what else?
Yes, we're going to be looking at Al Gore's new climate reality project, a couple of interesting recent papers, the launch of a green growth campaign called Pure Advantage in New Zealand, and
a tiny electric aeroplane that goes really, really fast. That's all coming up on this edition of The Climate Show. This episode of The Climate Show is brought to you by Celsius.co.nz, HotTopic.co.nz, SkepticalScience.com, Scoop.co.nz, and Kiwi FM.
Drop in the ocean. What good is a drop in the ocean?
Welcome along to The Climate Show. This is episode number 16, recording July 13th, 2011. It's your two-weekly dose of climate change policy, news, science and politics. And I'm, of course, your host, Glenn Williams, recording in the Kiwi FM studio in Ponsonby, Auckland City. My co-host, Gareth Ronaldo in Waipara, North Canterbury, New Zealand. Hello, Gareth.
Hi, Glenn. How are you?
Very good, very good. And you've just come in out of the rain to get out of the rain, obviously, but also you've been pruning the vines today.
Well, not the vines, no, it's the roses. You see, She who must be obeyed issued an instruction that the roses were to be done. So, given that we've got some hundreds of them, it being quite a large garden, I have, got stuck in.
I don't pretend to know anything about...
It's a thorny problem, are roses.
It's a thorny issue, yeah. I don't pretend to know anything about roses, but some say, well, you can't do it too early. You can't prune them too early.
No, I would usually do them in August, but as we discussed in the last show, I won't be around in August, so they've got to be done now. And the vineyard will start soon. We'll probably be starting on them at the end of the week, so... Winter is here.
It certainly is. Well, we've got a great show lined up. Today we're talking about ocean acidification with our special guest, Professor Keith Hunter.
Yes, Keith's a real expert in this field. He's probably New Zealand's leading expert and certainly a world-renowned scientist in this field. So it's going to be great to have Keith on. He's been very involved with the Royal Society of New Zealand's various statements on climate change. So it'll be good to have a natter with him to find out the state of the oceans and perhaps something about the state of the scientific debate such as it is in New Zealand.
Yeah, but no John Cook today. We won't be debunking the skeptic, but we will be, of course, moving on to solutions at the end of the show. But why don't we just crack into the news?
No. Yeah, I think we probably should. I was just going to say that John's gone to university for a day, which is always a good thing.
Always a good thing.
But we'll have him back in a fortnight. But yes, but the news, and the first item of news is, of course, that Australia has finally bitten the carbon pricing bullet.
Yes, so they've done what New Zealand has been unable to do. It's not a popular policy over there in Australia. In fact, I think I saw a stat this morning that 60% of Australians were against this carbon tax, and they also thought that it would negatively affect them personally.
Yeah, that's right. It's been an intensely competitive political debate in Australia with the skeptics and Australia is rife with skeptics, moaning about it not being necessary, about it being a stealth tax and all sorts of things. And of course, the political difficulties associated with Kevin Rudd being deposed by Julia Gillard and her statement that she would never introduce a carbon tax. And here we are, we've got a carbon tax, or Australia will soon have a carbon tax. Initial cost will be 23 Australian dollars per tonne, which will rise 2.5% per annum until the whole thing turns into an emissions trading scheme in 2015. So it's interesting. It is effectively an emissions trading scheme, and the initial price is roughly double what the New Zealand ETS emissions trading scheme current price is capped at $12.50 a tonne. So it's roughly twice as expensive for emitters in Australia, but it's only being paid by the 500 biggest emitters in the country. There will be price ceilings and floors when proper trading starts. Agriculture is excluded, but agriculture can benefit from various forms of carbon farming. And in order to make the whole thing kind of neutral, or as not very expensive for most people, they've also built in lots of changes to the overall taxation system. So tax-free thresholds for Australian taxpayers will almost triple to $18,200 from July the 1st, 2012, and then increase again in 2015. So effectively, they're giving everyone a tax cut, an income tax cut, in order to compensate for the increase in carbon costs. But they've also excluded the sort of transport fuel sector, which is included in New Zealand. So there are a number of sort of considerable differences between the two schemes. But what is at least common is that people who are operating in New Zealand and in Australia now face, at least at the margins, a charge on the emission of carbon. And although it might not have a big effect straight away, what it ought to do is have an effect on how people plan in the future, so that if you were thinking of expanding in a carbon intensive way, then knowing that this is built into the future pricing, both in Australia and New Zealand, should gently nudge the economy in the right direction. Now, if you wanted to be cynical about it, and if you wanted to say, as we do from every show, in fact, that we are facing a really serious problem that needs a really serious solution, you could say that the rather weak ETS in New Zealand and this, although it's comprehensive, it's not what you'd call hard-hitting scheme in Australia.
Well, what in saying that, what has been the general reaction from the scientific community?
It's been welcomed. It's been welcomed almost unanimously in the academic community in Australia. But I think it was welcomed in the same way that the ETS was welcomed here, which was that, yep, it's good that we've got one. It's a good start. It's not enough, but at least we're on the right road. And I think that would be a fair summary of the majority of opinion from people who are concerned about climate change in Australia. Obviously, the people who have been whinging against it, not wanting and whinging about carbon pricing, are incensed by it. And you could say that roughly the Murdoch-owned newspapers are causing a bit of a fuss, but then they're not exactly on a very strong wicket at the moment. The Murdoch media empire.
Yeah, indeed. We haven't introduced a carbon tax here in New Zealand, but there is a move from the business sector to green the New Zealand economy. They've just released something called the Pure Advantage campaign.
Yeah, it's built around a concept of green growth. And this particular group, the Pure Advantage Group, is kind of born originally out of business consultations that the Labour government a few years back set in motion. And some of the same people, like Stephen Tindall, who founded the Warehouse retail chain, Jeff Ross, who started up the 42 Below vodka company, have been involved in this. And they, over the last couple of years, have been lobbying the government very hard to try and encourage green growth, smart technologies, trying to get John Key, the New Zealand Prime Minister, and the rest of the cabinet to realise that strategically this is the way the country needs to move. And they did get something, and we'll look in a minute at, they got the government to kind of nod in that direction by setting up a green growth advisory group. But they've now gone further and launched this Pure Advantage campaign. And the idea of the Pure Advantage campaign is actually to sell to the New Zealand public and to the New Zealand business community the idea that being green and building green concerns into your business is not just something that you ought to do because it's the right thing, but it's where the growth is going to be in the future. And so if we start working in this direction now, then as the market really takes off, we'll be kind of ahead of the game. And the numbers they use are really quite astounding. They talk about the green smart technology area now being already globally $6 trillion per annum, bigger than defense spending globally, for instance. And that, it's a huge market opportunity for us, both in our own country, but in terms of exporting our expertise to Australia. Now they're going in that direction, but Japan, Korea, Taiwan, Singapore, US, you name it, it's a huge opportunity. And what they've done, because they're a business group and these are guys who are used to making money, they know about marketing. Pure Advantage has been set up to market this concept of green growth to the New Zealand public. And if the New Zealand public can get on board with green growth, then the politicians will follow.
So there's an opportunity here for New Zealand, and I've heard this, I think, spoken by one of those business leaders, to become the Silicon Valley equivalent of green tech, the whole of New Zealand.
Yeah, absolutely, and agriculture, because we are an agricultural nation. It's still the largest chunk of our exports comes in agricultural products, dairy, and so on. And the expertise that we've got scientifically in this field, and in terms of our management and abilities to run agricultural enterprises, that's a highly exportable thing. And if we can make sure that agriculture moves in the direction of green growth, as opposed to trying to maximize income at all costs and ignoring emissions, then we've got this opportunity, highly exportable expertise that we can send to the rest of the world. And it's interesting that just in this last week, Federated Farmers has elected a new president, a guy called Bruce Wills. I keep wanting to call him Bruce Willis, but he doesn't shave his head.
Yeah.
And he's an ex-banker who has gone back to the family farm over the last 6 or 7 years, and got himself involved with Federated Farmers, and seems to be rather more, how shall I put this, caring about environmental issues than the previous president, Don Nicholson, who was an openly declared climate skeptic and is now apparently wanting to stand at the next election for the far-right ACT Party. Yes.
Indeed. Well, if you want to go and check out what is behind this campaign and what they are planning, of course, we'll always have the links in the show notes, but you can check out pureadvantage.org.
And they're looking for people to support them. You can go there and sign up. They've got a pretty slick site. They've got all the social networking goodies. I don't think they've got a Google Plus account yet, but they've certainly got Facebook and Twitter. And they've got a YouTube channel with some interesting videos on there describing how the campaign goes forward. At the same time in the same week that the Pure Advantage campaign was launched, the government's Green Growth Advisory Group, which, as I said earlier, kind of grew out of the lobbying efforts of the Pure Advantage guys, issued its first discussion document. And I'd urge anyone in New Zealand who's listening to or viewing the show to go and have a look at that, because it's aimed at small and medium-sized companies, and the idea is to feed into the Green Growth Group ideas about how small and medium-sized companies can begin to look at green growth, how they can build that into their future planning and into their current operations. So it's perhaps a little lower key than the Pure Advantage thing. In fact, it's so low key compared to that you probably wouldn't have noticed it. I certainly didn't get a huge amount of press coverage. But it's a worthwhile effort, and the more feedback that the group gets from the New Zealand kind of business community and the general community, then the better, the more likely it is that that sort of green growth thinking will become important in government circles. So well worth going to have a look at that as well.
Okay. All right. Well, moving on, we're off to China now, where China's power stations will generate a future spike in global warming.
Yeah, that's a rather typical headline from the Independent newspaper in the UK, which has been the UK newspaper that's been most kind of upfront about climate change. It's put it on the front page very regularly. What they're reporting on is a paper. One of the authors is a guy called Simon Lewis from the University of Leeds, and basically what they did was they looked at the aerosols that had been emitted over 1997 to 2007 in China. Now, aerosols are the kind of pollution that comes out of chimneys, and it can have a cooling effect. So the best example is when Mount Pinatubo exploded in the early 90s. It ejected so much sulfur into the stratosphere that it cooled the Earth for about 18 months afterwards. Now, the huge growth of coal burning power stations in China, and they've been building them at an amazing rate over the last decade, has created this kind of pool of pollution over China, and it's of course spread around the world, and this has had a net cooling effect. So what this paper says is that the amount of aerosols being emitted from China over the last decade has, if you like, put a bit of a cap on global temperatures. So one of the reasons why we haven't had kind of a big spike in global warming in the last 10 years is that we've had the solar minimum, we've had all these aerosols from China, and the net effect has been to kind of slow the warming down. So what the Independent means when they talk about generating a future spike is that as China moves, as it is very aggressively moving towards cleaning up the new power that it's putting in and using more and more nuclear power and solar power and so on, as those aerosols reduce, then you're likely to see an increase in the rate of global warming. It's like taking the cap off, bang, up will go the temperatures. And that's something that we've known is likely on a longer timescale, because we do know that the amount of aerosols that are currently in the atmosphere, prior to this paper anyway, we believe that it was roughly, if you look at what they call the CO2 equivalent of all the greenhouse gases in the atmosphere, at the moment it's about 450 parts per million in terms of the warming effect. But the aerosols compensate for a big chunk of that, and so that the net effect is about the same as the CO2 level in the atmosphere, about 395 parts per million CO2e. So aerosols have been doing us a big favor, and we know that as we clean them up, that is going to unleash a certain amount of warming.
So those aerosols, they don't stay present in the atmosphere for as long as the carbon dioxide does?
Oh, absolutely not. The carbon dioxide has a lifetime of hundreds, if not thousands of years. So some of the carbon dioxide that we put up into the atmosphere today will still be there in 100 years' time, and in possibly even 1,000 years' time. It's got a very long tail.
But how quickly do those sulfates dissipate?
Very quickly. They can be gone in months, weeks, months, and years. So that with the Pinatubo thing, basically the aerosols cleaned themselves out of the atmosphere in about 18 months. The cooling effect was more or less over and done with in that time. So you could imagine that if there was, if China stopped burning coal tomorrow, then the atmosphere would clean itself up over a period of time, and we would see a spike in warming. So that's what the Independent was talking about when they talk about a future spike. But it does point up to a real problem that doesn't get thought about, or just certainly doesn't get discussed very much, and that is that this it's what we talked about with Jim Hansen a few shows ago, the Faustian bargain that we've made with aerosols, because what we have been doing by polluting the atmosphere in this way has actually been limiting some of the effects of global warming from the greenhouse gases that we've been putting in. If we clean up one without taking action on the other, we'll actually increase the rate of warming potentially quite dramatically.
Okay, well, let's move on to a story from Nature Geoscience, where they say state-of-the-art climate models are largely untested against actual occurrences of abrupt change, and is hugely befaith to assume that simulations of the coming century with these models will provide reliable warning of sudden catastrophic events. Warning, I should say.
Yeah, that's right. This is a paper in Nature Geoscience by Paul Valdez. It's a commentary, actually, rather than a paper. And it's, I wanted to talk about it mainly because it's kind of flown under the radar for most of the web that, or the climate web that you know, the blogs and so on that I read on a regular basis. And I thought it was very interesting because what Valdez does is look at 4 examples of past abrupt change. One of those is the Paleocene-Eocene thermal maximum, which was a period about 56 million years ago, when there was a very rapid warming event. Models don't seem to handle that terribly well. They don't handle the process of rapid desertification, that's a good word, isn't it? When the Sahara basically stopped being a nice wet place and became a desert about 5,500 years ago. Then collapses of the Atlantic meridional overturning circulation, which is an ocean process in the North Atlantic, which can, if it stops, it results in cooling in Western Europe, for instance. And those happened repeatedly over the last 120,000 years. 6 events, in fact, commonly called Heinrich events. And the models don't handle those. You can create a Heinrich event in the models, but you have to put too much you have to give the system too much of a nudge to make them happen. And then there's, so taking these events and looking at the way the models handle them, what he says is that we shouldn't be too comfortable looking forward that the models will be able to tell us about future rapid change. If you look at the sort of, it's one of the things that concerns me when I look at the graphs that come out of the IPCC's 4th report. We look at the model projections through to the end of the 21st century, and they're sort of smoothly rising lines. Yeah. There may be a bit of a wiggle in them, but they end up 2 degrees, 3 degrees, 4 degrees warmer at the end of the century than at the start. And we kind of assume that over the next 100 years, things are going to go along those lines. It's going to be 2.2 of a degree Celsius warmer every decade, and we'll end up with a much warmer climate at the end of the thing. What this commentary talks about is the surprises that could be in the future that the current generation of models are not able to give us warning about. And it's the climate's ability to respond to relatively small nudges, but with fairly dramatic changes, that should be giving us some cause for concern. So we shouldn't assume that warming will necessarily be gradual, even if it is fast, in geological terms. It may be that we will cross thresholds that will cause the climate suddenly to flip, not necessarily on a global level, but on a regional level. And what was currently green farmland could become a desert in the space of a relatively short period of time. So I just thought that was an interesting, it's an interesting article. It's not too difficult to understand, well worth looking at. So a bit of a plug there. That's the most sciencey little bit that we're talking about this week. Until we get to Keith and his equations, of course. Yes,
that's coming up very shortly. But we've got our last news story, and I just noticed this one pop up this morning. Al Gore, Mr. Inconvenient Truth. He's back with Inconvenient Truth 2.0. Well, actually, he's not calling it that. He's calling it the Climate Reality Project, and it's going to be kicked off with a 24-hour live streaming event on the 14th of September, and the day's events will include a new multimedia presentation by Gore, so he's taking it on the road again, that will connect the dots between extreme weather events and climate change. The website is climaterealityproject.org. Choose reality, it says on the front page, and it's got a wee countdown there, and you can watch the video, spread the word, take action. So it's all going to be happening in a bunch of cities around the world. And basically it's his, I suppose, anger at the way the science has been presented by skeptics over the years since he released Inconvenient Truth. And now he's basically just saying, look, what can we change? We need to change things right now. We need action right now. So it looks like a very cool project. It's a great wee website. And being Al Gore, of course, he's managed to put together a wee promo video for the 24 hours of reality, they're calling it as well. And here it is here. It's just a short wee promo.
A street can become a river. A mountain can become a mudslide. A forest can become kindling. Across the globe, cataclysmic weather events are occurring with such regularity that it's being called a new normal. But there's nothing normal about it, and there's something else that lies destroyed amid the rubble, the truth about climate change. Big oil and big coal are spending big money to spread doubt about climate change. They've been able to do so quietly, but not anymore. On September 14th, the world will join hands to create 24 hours of reality, an event that will focus the world's attention on the full truth, scope, scale, and impact of the climate crisis. To remove the doubt, reveal the deniers, and catalyze urgency around an issue that affects every one of us. Climate change is not your fault. The climate crisis is our problem, and real solutions can come when we address it together. Fossil fuel interests have money, influence, control, but together we have something that they don't. Reality. Join us for 24 hours of reality and show the world what can change in a day.
Dum dum dum. There you go. And no doubt, the place not to go and discuss that video is YouTube. I wouldn't recommend getting into a debate on YouTube comments. That's for sure.
Yes, I think generally speaking, more power to Mr. Gore's elbow, because he is doing serious work here. This is slick stuff. It's a global event. We're talking about using 24 presenters in 24 time zones over the period of one day. And the ticker on the front of the site says that's 63 days and 23 hours away at the moment. So it's good. I like the idea that there's an updated presentation, and that they will be taking regional. So they are planning to do something from Auckland.
Yeah.
If they've got China, they've got Japan, they've got Korea, they've got Indonesia, they've got something in the Middle East, India, Iceland, Greenland, the US, of course, all over the world. And I think that's good, because it is a global problem that requires a global solution. And the only thing that concerns me about it is that, funnily enough, whilst I think Al Gore has done a fantastic job, he is such he is so hated by skeptics and the American right, and they, to get to one classic skeptic argument is Al Gore is wrong. Now, to anybody outside the US, Al Gore is an vaguely interesting sort of former American vice president, and but the spitting fury that he can generate amongst American climate skeptics in particular, which seems to have infected many other parts of the world, unfortunately, I don't think it helps him terribly much. All this furious invective that gets directed at him, so that may, to a certain extent, work against his 24 hours of reality, the Climate Reality Project. But look, it's a fantastic thing that he is carrying on doing this, and that he's raising money and putting together slick campaigns. And ultimately, just as I said, we were talking about the Pure Advantage and green growth issue in New Zealand. What we need to do is to develop campaigns that empower politicians to do what they need to do. And if we don't empower our politicians and tell them what it is they need to do, and make them realize that there are votes in doing the right thing, if we don't do that, then we ain't got a solution, because the solution has inevitably got to be political.
Indeed, indeed. Well, look forward to seeing how this project develops over the next few weeks. And we don't even really know what's even happening in our local centre, Auckland, at the moment. There's a wee page there, but it hasn't really got a whole lot of information. And we're not even sure exactly whether or not the page is even correct the way it's written. But I'm sure that'll get.
I think
updated.
if there's anybody involved with the Climate Reality Project who happens to be listening to this, you do need to rewrite your Auckland page, chaps.
Yeah. All right, that's our news. So, time to bring on our special guest for today's show. It's Professor Keith Hunter. Now, he is New Zealand's leading scientist in the field of marine and freshwater chemistry. He's based at the University of Otago. He also directs the joint NIWA University of Otago Centre of Excellence for Chemical and Physical Oceanography, based in the Department of Chemistry. And Keith Hunter's with us today, I think, in the bowels of Otago University. Hello, Keith.
Hello, Glenn.
Hi, Keith. It's Gareth here. Welcome to the Climate Show, episode 16.
Yeah.
And we're going to talk to you about ocean acidification and what that means for us as we move through this century. So, wondered if you could start by giving us a very basic overview of what's going on.
Sure, Gareth. I mean, maybe 25 years ago or 30 years ago when I was a student, one of the hot topics was called missing carbon, and it was based on the observation that if you compared the CO2 increase in the atmosphere with the inventory of fossil fuel emission, about half was missing. And a lot of us in ocean sciences thought maybe some's going into the ocean. And I think to cut to today, we've now known for at least a number of years that the surface layers of the ocean have absorbed probably about a third of the carbon released by combustion of fossil fuels. And that absorption, it's really restricted only to the upper part of the ocean that is in intimate contact with the atmosphere and equilibrates over a time scale of no more than a few years, where that carbon dioxide is penetrated. And of course, once it's gone into the ocean, it doesn't sit around as CO2. It actually undergoes reactions, because CO2 is an acidic gas, so any acid will go looking for a base to react with, and the most abundant, or at least the most reactive abundant base, is its cousin, if you like, the carbonate ion. So the two combine together.
So what happens when a molecule meets the water? What's going on in terms of why does it go in? Why does it come out, as it were?
It's because there's a concentration gradient, and for gases we measure concentrations in terms of pressure or partial pressure. So prior to humans combusting fossil fuel, the ocean and atmosphere would have been in equilibrium, and we can measure the pressure of CO2 in the atmosphere. We do that. We can also measure the equivalent value for water. We just take some water, put in a little bit of air, let it equilibrate, and measure how much CO2 is in the air. So if the CO2 pressure of the water is less than that of the air, then there's a concentration gradient driving carbon dioxide into the water, and vice versa. And over the ocean surface, there are some regions where that gradient is from air to sea, and even some regions where it's from sea to air. But the net effect, averaged over the whole ocean, is that because we've increased the CO2 level from about 280 in pre-industrial time to almost 400 now, the ocean is well out of sync overall, but the surface ocean appears to have kept up. So the deep parts of the ocean, in most parts, have not yet encountered any of that extra CO2.
Okay, that would have parallels with the deep oceans warming too. It takes time for the upper layer of the oceans to move that heat into the deep.
Yes, that's absolutely correct. Yes, exactly the same or a very similar process.
So talk us through the chemistry. What's going on when a molecule of CO2 meets the top of the ocean?
Well, it goes into the ocean principally because prior to us burning fossil fuels, the ocean and atmosphere were essentially in equilibrium, and the quantity we often measure in seawater we call the partial pressure, which you can think of as being the pressure of carbon dioxide that it would have in air in equilibrium with the water. And you can compare that directly with the pressure of CO2 that you actually have in the air. I should add, we measure concentrations of gases usually by pressure rather than other units. So that's why I'm talking about partial pressure.
Yeah.
So the partial pressure, we increase CO2 in the atmosphere, the partial pressure goes up. That's greater than the seawater, that drives it in. Now, once it gets into the water, it's immediately out of equilibrium with the chemistry of the water, because CO2 as a molecule is not the only form present. In fact, it's a very minor form, but it's got two what you might call chemical cousins. The bicarbonate ion, which everyone's familiar with in bicarbonate of soda, that is carbon dioxide, which has been combined with 1 unit of acid to become bicarbonate. And then there's the carbonate ion, which is you'd be familiar with in things like washing soda or indeed limestone. Now, carbonate is a base, a very good base. And carbon dioxide or carbonic acid is a very good acid. So the two immediately react with each other. So the net result of CO2 entering the ocean is that most of the CO2 or carbonic acid, they're the same thing, disappears. An equivalent amount of carbonate disappears, and both of them get turned into bicarbonate, which is, if you like, their middle species. And because 99% of the carbon dioxide in the ocean is already present as bicarbonate, you get a very small change in the amount of bicarbonate. So the net effect is carbonate goes down, which threatens calcifying organisms, because as the carbonate concentration decreases, then they will eventually reach a point when there isn't sufficient carbonate ion to prevent them from dissolving.
Okay.
And the pH goes down as well.
So that sort of lowering of carbonate's already been observed.
Most definitely, yes.
Yeah.
There have been several time series stations around the world, one in Bermuda, one in Hawaii, and we've been operating one across the Otago Shelf as well, and they all definitely show a decrease in pH, a decrease in carbonate ion concentration. So the longer term thing is what happens when calcium carbonate gets involved, and that's where we might have a look at equation 1 that Glenn's got.
Equation 1 coming up.
Great. Thanks, Glenn. Now, you might have noticed we've been running a post recently on skeptical science, and we started it out based around this equation, which I think Doug described as the E equals mc squared of ocean acidification, and I think it really is true. In my experience, this is the most misunderstood chemical equation that's relevant to ocean acidification that there is. What we're describing in this equation is how calcium carbonate is formed in the ocean. And it's formed by the combination of 2 bicarbonate ions. Remember, that's the majority of the carbon dioxide, and a calcium to form calcium carbonate, carbon dioxide, and water. And so the conclusion from that is when you manufacture calcium carbonate in the ocean, you also generate carbon dioxide. Now, most people find that a showstopper. They just can't accept it. But from a chemical point of view, it's perfectly obvious. Calcium carbonate is a base. If you remove a base from seawater by precipitating it as a solid, then you leave the seawater more acidic, because the overall acid-base balance has to remain the same. When you make seawater more acidic, then bicarbonate ion turns into CO2. Now, the best way to understand that is to look at the same equation written backwards, which is we've labelled number 4. If we could look at that, Glenn.
There we go.
Now, I get a lot of people writing and saying, but where did the white cliffs of Dover come from? That's all calcium carbonate. That shows that the much higher CO2 levels we had in the past, got all soaked up by the ocean and formed all this chalk. Well, that's not right in the sense it's focusing on the wrong part of a cycle. So this is the reaction in reverse. And this is telling us the story about where the bicarbonate comes from in the ocean. Calcium carbonate, limestone, reacts with rain. And rain consists mainly of water and dissolved carbon dioxide. So rainwater is actually quite acidic. Its pH is about 5. And so it slowly dissolves up the limestone and produces calcium and bicarbonate ions. And that's what we call weathering. Now, rivers consist mainly of calcium bicarbonate. Those are the two most abundant ions in rivers. And so that stuff is going down the rivers and getting into the ocean.
Right.
Now, that's where the calcium bicarbonate in the ocean comes from. Now, a really important question, which is I put to all students when we teach them marine chemistry, is if we estimate how fast bicarbonate is entering the ocean through weathering of limestone, how long would it take to use up all the CO2 in the atmosphere? And that's an easy calculation to do. We know how much CO2 is in the atmosphere. We know how much bicarbonate is present in rivers. And the answer is very surprising. It's 3,500 years. Now, quite obviously, quite obviously, that can't be the full picture because the atmosphere would have run out of CO2 right at the very beginning, billions of years ago.
Yeah.
So it follows that weathering reaction where the calcium carbonate and CO2 combine together on the continents has to be reversed again in the ocean. So you have to form calcium carbonate and you have to get the CO2 back so that you can replace the CO2 that was used in the weathering in the first place.
So those two equations are essentially perpetual. They just revolve and go round and round and round.
And that's the carbon cycle in a nutshell. Those are the key parts of the inorganic or non-biological carbon cycle, although the formation of calcium carbonate is itself biological. But if you like, it's the simple chemistry of the carbon cycle. And it's what I call a climate thermostat, because you can see that process, the balance between weathering and the formation of limestone in the ocean, controls how much CO2 there is in the atmosphere. And so that is the process that regulates climate over timescales of 10,000 years and longer.
And that's also presumably why we talk about the CO2 that we're putting into the atmosphere having a very long atmospheric lifetime.
Absolutely.
On the scale of thousands of years.
Yeah, because the process that takes it out is weathering.
Yeah.
Okay.
And weathering happens on that sort of scale. The ocean can only absorb so much. And in doing so, it actually doesn't matter whether the weathering occurs on the land or in the ocean.
Okay, so I guess the big question, though, is how does this translate into bleached coral, which is some of the results that we hear of ocean acidification?
Well, I think some of the coral bleaching is related to temperature. I understand that they get a bit too warm for the algae that they contain, and if the temperature range isn't right for the algae, then the coral eject them, and that's how they bleach, because corals are a mixture of coral organisms and the symbiotic algae that are in them. So where ocean acidification is important for coral is that it relates to whether or not they can form their calcium carbonate skeleton. And it's been shown, for example, in some extreme experiments where corals were grown at quite low pH, 7.4 I think it was, that they lose their skeleton altogether and they can still live all right. But of course, in the real environment, corals have their calcium carbonate for a purpose. It's to stop people eating them. and so when you're a naked coral polyp with no shell, you'd probably be a pretty tasty meal for a fish.
Now, in terms of the global ocean, there are lots and lots of creatures, carbonate shells or skeletons, aren't there? All plankton and zooplankton, all sorts of things. So can you tell us a bit about that?
Yeah, well, there's a whole variety. In fact, it's a whole witch's brew of biochemistry, much of which we don't yet understand how exactly these organisms calcify. They're extremely clever in terms of the structures they build, and they defy the ability of a chemist like me to reproduce those structures. All I can make is a nice calcium carbonate powder. But there are various minerals involved. There's no single calcium carbonate, and there are a couple of common ones. Are called aragonite, which is pretty common in many shellfish, and is also the material used by pteropods, which are a species of Southern Ocean snail, which is quite important in the food web. And then there's the mineral calcite, which is the most stable of the, we call them polymorphs, or different minerals. So these minerals all have the same chemical formula, and they differ in the way the crystal structure is put together, and that affects things like their solubility and their stability.
Okay, so these little creatures have mastered the art of making minerals.
Oh yeah, they have, and they've done it obviously largely as a means of protecting themselves against predation.
Yeah.
And for bigger organisms to provide some kind of structural stability. I mean, we do the same. We use apatite instead. So we've got a skeleton. We have an internal skeleton made of calcium phosphate. But virtually all vertebrate organisms, do some form of use some form of mineral to do that. It's a structural purpose.
So when we pump carbon into the ocean, what we're effectively doing is upsetting the balance of the brew that these creatures use to make their skeletons.
Yes, that's true. And so the big questions that we're facing is what will the effect be? We know that some people have said, the concentration of carbonate can be driven so low that the shells will dissolve. Theoretically, that's true, but practically it's different, because we do know that organisms are capable of creating their own microenvironment for the manufacture of biominerals. The classic example of organisms that do this, which even many of my colleagues forget about, are the diatoms. The diatoms make silicon dioxide instead of calcium carbonate, and silicon dioxide is permanently undersaturated in seawater. So theoretically, it's difficult to form, but the diatoms have figured out how to do it, and they do it by creating a membrane around the cell that protects the mineral from dissolution. So they create an internal seawater environment that differs from the outside. So it's almost certain there will be calcifying organisms that can do the same thing. So reducing the pH may make it harder for them to calcify, and they will have to expend more energy to do it, but it may not make it impossible.
Okay, but I guess what we're doing is we're fiddling with the ecology and all the interrelationships between these organisms.
Well, exactly, and I mentioned the what I call the climate thermostat before, and how it regulates atmospheric CO2. Well, one of the other things it regulates at the same time is the concentration of carbonate in the ocean. And so by adding carbon dioxide to the ocean, as we've been doing, we're disturbing that as well. We're making carbonate ion less available, and it won't be until enough calcium carbonate has dissolved, either by dissolving limestones on the land or dissolving limestones in the ocean. Once that's restored the balance again, then things will go back to the original carbonate ion and carbon dioxide levels. And the problem we have is the time constant for that is just so long. It's maybe 100,000 years.
Wow. So do we have any way of knowing what the oceans were like in previous warming episodes? Have the oceans have got more acid in the past? Can we dig it up and find out?
They have, yes. And there's one particular event which took place 55 million years ago. It's called the Late Paleocene Thermal Event. And what appeared to happen then was some warming, probably in shelf seas, led to what you might call a runaway release of carbon from the carbon cycle, probably a lot of it being methane frozen in sediments as methane hydrates.
Yep.
So we think that something like 5 or 6 thousand gigatons of carbon were released during that episode, probably over 1,000 or 2,000 years. That, in context, that's probably 20 times the amount of CO2 we've released now through burning fossil fuel. And the various isotopic and related measurements, in sediment cores show what happened then was certainly catastrophic. 90% of marine calcifiers became extinct. Many were probably driven into cyst stages and had to wait out the changes, the resumption of the original chemistry. It took about 100,000 years for the carbon cycle to get back to normal through this mechanism I talked about. In fact, what happened was excess weathering got rid of the carbon dioxide and restored the original situation. A lot of huge temperature in the Arctic was as high as 20 degrees Celsius.
Do we know what the tipping point or trigger point was back then?
No. I mean, I'm not an expert on this, but there's still a lot of uncertainty surrounding why the event started in the first place.
So what's the prognostication then for the next 100 years? What sort of increasing acidification can we expect if we continue with business as usual?
Well, there have been predictions made on that, and people have talked about a decrease in ocean pH of another 0.3 to 0.4 by the end of this century. That will certainly take us into a pretty uncertain regime for calcifying organisms. And that, I think, would probably be pretty serious for corals. It would certainly be disastrous for pteropods, which means there'll be a niche opening up in the Southern Ocean food web because they're a key part of it. And the real questions are, can something else move in and fill that niche without having a major effect on the higher predators who depend on them for food? Having said that, there are going to be a lot of organisms that will benefit from lower pH, because when you look at this carbon cycle in a longer context, the Earth has been slowly cooling down over probably the last 60 million years because of an enhancement in weathering caused by the collision of India with the Asian continent. So if you go back earlier in that, India was part of the big Gondwana land, along with Australia and Antarctica. And then it broke off and drifted north and banged into Asia and formed the Himalayas. And that broke open the Earth's crust and exposed all sorts of new rocks. So there's very clear evidence that weathering has increased prior to from that time, and that's led to a slow increase in ocean alkalinity, and it's led to a decrease in atmospheric carbon dioxide. And during the course of that, of course, a lot of organisms that lived, I'm thinking of photosynthesizing organisms like plankton, were adapted to a much lower pH in the ocean. And of course, at a lower pH, free carbon dioxide is more available. And many organisms found it increasingly difficult to photosynthesize because they couldn't get enough free carbon dioxide. And so that led to a number of interesting evolutionary strategies, and one of which was the development of enzymes like carbonic anhydrase, which are very characteristic of more recent organisms. And these enzymes enable plankton to access bicarbonate ion, which, if you think about it, it's a pretty sensible thing to do because it's the most abundant form. So what will happen is that as pH goes down, the metabolic cost of using an enzyme like that might outweigh the advantage of being able to access free carbonic acid directly. So you might get a shift, and this is exactly how evolution works. Is one species gets an advantage over another, its genes proliferate in the following generations.
But
so,
is there a risk, though, at the moment that the change is so rapid that there is no time to evolve?
Well, what I'm saying is that many of these organisms that don't have a carbon concentrating mechanism like carbonic anhydrase, and there are others, may still have the ability to function. In other words, if they've still got the genes needed to access CO2 directly, or if they're still working that way, then it will be just like feeding them fertilizer. They will say, great, and they'll grow. Whereas if you take a very common organism, Emiliana huxleyi, which is a coccolithophore.
Those are the things that we sometimes see pictures from space of great swirls of milky water.
Yeah. Oh, yeah. Okay.
Now,
yeah.
E. hux is a very modern organism. It's only a few million years old. And so it's never been adapted to a high CO2 world. Whereas there are many coccolithophores that are 2 or 250 million years old, and probably, if they haven't lost their genes for those functions, are probably better adapted to a lower pH world.
So we really are talking about a soup, aren't we? A future soup.
That's right. But the really important issue is we think of the ocean. We don't think of phytoplankton. We think of fish, and whales and dolphins and sea lions because they are the obvious ones to us, and some of them are kind of cute, and we like to eat some of them. But they're really a very small part. They're like the lions and tigers of Africa. The really important organisms in Africa are the prairie grasses that the herbivores feed on, and who supply the predators. So, and of course, we're very much a predator of the ocean. So we might have to learn how to eat plankton.
Crikey.
Yes, absolutely. I mean, in our last show, we talked about a report on the state of the oceans that was prepared by a group recently. And it made pretty depressing reading, because acidification is not the only pressure that we're putting on the oceans. There's overfishing, there's pollution, there's all sorts of stuff going on.
Yes, that's very much it. It does make depressing reading. I have got a little bright note that I thought I'd mention.
Okay.
It's an exercise I've been involved with recently with a group called GAZAMP, which is a United Nations Environment Programme group of scientists, called the Joint Group of Experts on the Scientific Aspects of Marine Protection. And we had a working group looking at the broad topic of chemical substances going into the ocean from the atmosphere, and I got the job of looking at acidic gases. You probably you will have all heard of acid rain. And this is basically acids derived from sulfur dioxide and nitrogen oxides, and they've long been a problem in the continents for their effects on lakes and forest ecosystems and stuff. And there've been lots of controls put on emissions to try and minimize this, but the issue is still around, and it's particularly applicable to shipping, because until recently there were no controls over the quality of bunker oil used in ships, so they used all the really high sulfur oil. But the task that I was given was to investigate whether these acidic gases make ocean acidification worse, and intuitively you'd think that'd be the case. That if you add to the carbon dioxide sulfuric and nitric acids from the atmosphere as well, you'd expect it to make ocean acidification worse. Now, ironically, that's not the case. In fact, it eliminates ocean acidification. Wow. And and when I first got this result, I thought there's something wrong with my computer program. So I went back and did it by hand just to make sure it was right. So here's how it works. Sulfuric and nitric acid are strong acids. And we call a strong acid in chemistry one that reacts completely with things, whereas carbon dioxide is a weak acid. So if you put carbon dioxide in water, very little of it reacts with the water. Whereas if you put sulfuric acid in water, the whole lot reacts, and you don't have any sulfuric acid left. You only have hydrogen ions and sulfate. So when you add sulfuric acid and nitric acid to seawater, they look around for bases to react with. So they'll react with the carbonate, but they'll also react with the bicarbonate, which is very abundant. And when they react with bicarbonate, they produce carbon dioxide, which promptly finds itself out of equilibrium with the atmosphere. So over a period of months, it just vents straight out to the atmosphere. And the final pH change at the end of that is almost zero. The cost, of course, is that the ocean's no longer taking up the CO2. And in our paper, which just appeared in Geophysical Research Letters last week, we calculate the conditions under which this might happen, and we looked at 3 typical places. The North Sea, which is an area of very intense industrialization, but which there are lots of modern controls. The Baltic Sea, which is very susceptible because it's a very low alkalinity inland sea, and the South China Sea, which is probably getting worse and worse every day because of all the activities in Asia. And we found that these effects would all be quite measurable in those systems, and in fact that if the input of those gases was a bit higher than it is in the South China Sea, then their input would actually stop the ocean taking up CO2 at all.
Is this something that you can hang your hat on, though?
Oh yes, we're quite convinced this is happening. The chemistry is not complicated. It may sound complicated when you explain it in words, but if you look at the equations, it's
yeah.
That's interesting, because we were talking before we started this interview, Keith, about what Jim Hansen calls the Faustian bargain with aerosols. And we were talking about a recent paper where Simon Lewis at the University of Leeds had calculated that China's output of aerosols had kind of put a cap on warming over the last decade. And I'm just now trying to get my head around this fact that if so at the moment, China's coal burning is stopping us warming as fast as we might, but it might actually be changing the South China Sea in such a way that the CO2 stops being absorbed, so that will increase. This is getting very, very complicated.
Isn't it? Yeah.
Well, you can do a thought experiment, Gareth. If you were to capture all the sulfur dioxide coming out of coal burning power stations, and you were to react it with bicarbonate, you would generate CO2.
Right.
And that's effectively what this is doing, except that the CO2 is, you could argue, has come from the burning of the coal in the first place, and you're simply, so you don't gain anything. It's a Faustian bargain.
Yeah, absolutely.
But you can slow down acidification of the ocean, but all you're going to do is increase by a greater amount the amount of CO2 in the atmosphere.
Now, the other side of that equation, of course, is that if we were able to reduce the amount of CO2 in the atmosphere, and we talk about 350.org and Jim Hansen's 350 ppm for a planet that still has ice caps. At that point, as soon as we get down below where we are now, then we change the partial pressures, and the oceans will start giving us back carbon dioxide.
Yes, that's true, but you need to set against that the fact that that same surface mixed layer of ocean is also mixing downwards, and you can think of that as burying the excess CO2 into the deep ocean. So I would think you'd need to do a fairly detailed ocean circulation model to figure out which of those processes is going to be more important. The timescale for mixing the ocean would be of the order of a couple of thousand years. So if we go ahead and reduce CO2 more quickly than that, then you're quite correct. But if we go about it more slowly, as we probably will if we run out of fuel, then it may not be quite as bad as that.
Yeah, yeah. Well, it's an immensely complex subject, and as you said before, you have started an 18-part series, I understand, at Skeptical Science. I've read the first few. It's clearly a subject which demands a certain amount of concentration if you're really going to get your head around it.
Yeah, that's true, and I think what will be more useful will be the booklet that we'll put out at the end of that, rather than the series. But I think we kind of proved a point to ourselves that there are many, many steps in the arguments surrounding what happens in ocean acidification, and people get confused over almost every one of them. And it's been fascinating to see how the confusion arises. Not only, you can't blame people who aren't specialists for being confused about a lot of these things, but some of them who come in and comment appear to have some knowledge of chemistry, and yet are often missing the point. And we just hope that at the end of it we may have made some contribution to a clearer understanding of it all.
Oh, well, I think it's a fantastic and interesting experiment, really, to get three good academics publishing in this way. It's it's an interesting contribution. And the other thing is that, of course, the skeptics the people who argue against action on climate change have tended to kind of dismiss acidification as a problem. I think the Lord Monckton, Christopher Monckton, who is not a Lord, well, he may be a Lord, but he's not a member of the House of Lords,
yes,
is touring Australia at the moment, and I think I've seen presentations where he's just denied that acidification is happening or could be a problem.
Well, there's a lot of people like that. I remember once Barry Brill criticising me by saying that ocean carbon had never been measured and couldn't be modelled, which I found somewhat extraordinary. It made me wonder for a moment what I've been doing for the last 10 years. But, I don't pay much attention to that sort of criticism. Because it clearly is motivated by ignorance or an unwillingness to look at the evidence. I think the criticisms that we have oversimplified the effects of ocean acidification are valid ones. I think the more we work on it, the more complex we discover that the biological responses to acidification are quite complex, and that's a very fair criticism. But I don't believe that is an excuse for no action. I think that just makes us even more cautious about what's going to happen. I think there's no doubt there'll be biological changes. Whether they'll be catastrophic or not, we simply can't say. But it's certainly no excuse for not doing anything.
Would it be fair to say that the acidification as an issue like this is a relative newcomer? The climate community, atmospheric sciences, were talking about the atmospheric changes and the potential for climate change, 30, even 40 years ago in some cases. But acidification seems to have come onto the menu a lot later.
Oh, that's absolutely correct. And I have to say, for some of us, it's a bit embarrassing. When I give talks, I love to show a diagram I have, which shows the changes in ocean chemistry as atmospheric carbon dioxide is projected to increase. And I drew that diagram in 1983. And it shows very clearly that the pH is going to go down and that the carbonate ion concentration is going to go down. And it was a number of years before I realized what I had in front of me. The significance had completely escaped me.
Right.
And so I think it's the biologists who have. And so the ocean acidification effort that's going on now internationally is very much characterized by people from chemistry and physics and biology working together. And that's true particularly of our group down here at Otago, where we work very closely. The chemistry group works very closely with colleagues in both the Department of Botany and the Department of Marine Science. And it's been marvelous, actually, to be involved in that sort of thing, because I know really very little about the details of biology. I mean, I know what the difference between a plant and an animal is, and that's about it. But it's absolutely fascinating to learn, the things that these organisms can do and the variety of responses they have. And so for me, it's been a really fascinating new area of research.
Brilliant.
Well, Keith, that's been thank you for that. It's been a really fascinating introduction to the subject. And I can only recommend to our listeners and viewers that you go to Skeptical Science. And I think you've got 4 or 5 published now in that series.
Something like that, yes.
Yeah, and there's a lot more to come. And at the end of it, there'll be a very useful booklet with the basics of the science of ocean acidification. So thank you for that, Keith. Very, very grateful that you found the time for us this week. And you will continue to be our go-to man for ocean acidification in future as this subject develops.
Sure, no, that's fine. Great.
Thanks very much, Keith. That is Keith Hunter, who is from the University of Otago. And we're into the final section of the show. We call it the many-part solutions section. And first up today, we're looking at something called the Solar Promise.
Yes, that's right. It's a New Zealand development. It's a group of local authorities have got together. I think 9 councils and their mayors got together this week to announce that there was a campaign being launched called the Solar Promise. And the idea was to get people in these districts to use more solar power. That's everything from solar hot water. Well, it's mainly solar hot water, but obviously other stuff as well. And that includes the mayors of Hastings, the local government New Zealand President Lawrence Ewell, the Mayor of Wellington, Marlborough District, Tasman District, Dunedin Mayor Dave Cull, Tim Shadbolt in Invercargill, Gore District Mayor Tracy Hicks, and the Whanganui Mayor Annette Main. So a pretty good cross-section, not my mayor. I have to go and have a word with Mr. Mayor and get him onto this. But the idea was to make it easier for people to put solar thermal stuff onto their roofs, getting hot water, by reducing the costs of the consenting. This was done in Nelson very effectively, so that people can begin to enjoy the effects, the sort of reduction in cost as soon as the stuff goes up, rather than having to wait for what could be quite a lengthy payback period for a capital investment. So I wanted to draw attention to that, and there's quite a swish little website for the Solar Promise. Just an interesting development in New Zealand.
Yeah, well, hopefully they might be able to introduce what Google was doing with that company in the States that we were looking at a couple of shows ago, where you could lease the solar panels or rent the solar panels, and it would still work out to be cheaper for you to do that.
Yeah, that's right. I mean, we discussed, as you say, a couple of weeks ago, the idea that solar photovoltaic panels were getting cheaper and cheaper, and were very soon going to be, if not already, below the cost of electricity generated from fossil fuels. But the solar thermal stuff, which is basically solar hot water, can save you 40% of your electricity before you even start thinking about generating your own.
Yeah.
Because it's more or less a no-brainer. And I think there have been a number of schemes in New Zealand for putting solar thermal onto roofs with various degrees and varying degrees of success. But what struck me forcibly a few years ago, I went on a mushroom and truffle trip to Yunnan province in China.
It sounds like something you do in Vegas. A mushroom and truffle.
No. This was getting down and dirty in the forests of Yunnan, looking for mushrooms and truffles. For a truffle grower, I have to tell you, that's paradise. But we flew into Kunming, and as we were leaving which is the capital of Yunnan, as we were leaving the city, every building, the apartment blocks, the roofs were covered in solar hot water. These silver panels, which were, providing hot water for all the people in the apartment blocks, And when we got out into kind of remote rural districts, little countryside towns, every town in China has a bicycle shop, because that's how people get around in an awful lot of places. But in every little country town, next to the bicycle shop, there was a solar thermal shop selling solar hot water, because, they realized, I think the Chinese realized a long time ago, that the way to get kind of modern living standards out into the remote rural regions, you don't build great pylons to carry the power in. It's much cheaper, actually, if you can stick something on the roof or do it off the grid, as it were.
Yeah.
So it really struck me that, one of the reasons why I'm occasionally optimistic about China's ability to make a big turnaround in coal use is the fact that they are already doing lots of interesting things like this.
Okay, well, we love electric vehicles on the show, and maybe we might even love electric planes even more.
Yeah, absolutely. It's a fantastic little plane called a Cricri, which is short for cricket, I'm told, and it's basically the world's smallest kitset aircraft. And this particular French pilot has kitted his up with electric motors and batteries. So he's got two 35 horsepower electric motors and two 1.5 kilowatt hour batteries. And he managed to hit 175 miles an hour. And I think you've got the video there, haven't you?
Yeah, just looking at it, how its size compared to a Boeing, or it's tiny.
That's the A380. That's the Super Jumbo. And the plane's so small, the guy's virtually kind of wrapped up in it,
Yeah. And I imagine you'd be able to do some aerobatics in that, some pretty cool stunts.
Oh yeah. It's a very popular little plane, the Cricri, but the fact that he's got these electric motors in it is what makes this particular one so special.
Yeah. And I'd imagine it wouldn't make much of a noise either.
No, absolutely. You might not notice it coming. But the key is obviously the developing the battery technologies that would allow for the plane to fly for reasonable ranges. If this particular plane, when it's flown at about 65 miles per hour, can fly for about 25 minutes. So we're not talking about being able to cross the Atlantic or perhaps even cross La Manche or the English Channel, but it's still an interesting little thing. Certainly little.
Absolutely.
But we've talked about electric planes in the past, and I think we talked about the plane which managed to fly through the night on its own battery power with solar cells, and I think they're planning a round-the-world flight, non-stop solar powered flight around the world, which will be we'll have on the Climate Show as soon as we know more about it.
Indeed. Well, that wraps up the Many Part Solutions segment. Now, time for some feedback before we go. A nice wee email sent in from Victoria, and it says, I just wanted to say how much I like the Climate Show and to let you all know how far-ranging your audience is. I grew up in Washington, D.C., but I moved to northern Maine in 1981. The changes in our local climate in the past 8 years have been extraordinary, and the elderly people here all know that global climate change is real because of the weird weather. Unfortunately, people under 70 are more difficult to convince. I recommend your show highly to my friends, and I'll never get to New Zealand because I've been trying to limit travel, no air travel for several years. I travel by train, which is hard but not impossible in the US, but New Zealand looks beautiful on television, and I enjoy all the references you make to your local weather and geography. Thanks for all your work. That's from Victoria. Yeah, it's very nice, isn't it?
Yeah, thank you. Yeah, thank you for that. And it is always nice to know how many corners of the world we reach. I do enjoy that. And I hope we reach quite a few corners of New Zealand as well. But
Good. All right. Well, that about wraps up this edition of the Climate Show.
Very cookless edition.
It was another cookless edition. Don't forget there are many ways to... Yep. Next week, what?
Oh no! Next time it will definitely be a cookie version, so that'll be there.
Don't forget that there are many ways to enjoy the show as well, in video and in audio, and you can find all the subscription links on theclimateshow.com and hot-topic.co.nz. Don't forget there was also the web app as well through Stitcher. Go to Stitcher.com and you can download their app to your iPhone or Android device or BlackBerry or whatever you have, and you can find the Climate Show inside that as well. Any feedback you have, don't forget you can put that in the comments section as well at theclimateshow.com and hot-topic.co.nz. Any last words?
While we're on that social networking stuff, I mean, can you do a sort of show page in Google Plus? Is that possible, do you think?
Not just yet, though you can create a Google account for the Climate Show and then possibly create a Google Plus page out of that. But I think that they are rolling out business pages, and I'd imagine that would be for organisations as well eventually into the future.
Yeah.
So we'll get there.
We'll have to be patient.
We will.
All right. Well, look, thanks to everybody for listening to the show, and we'll be back in a couple of weeks, and we'll have John Cook, and we'll have another guest, and it'll be spanking full of wonderful and sobering information about the climate.
Can't wait for that spanking show. That's coming up next time. We're into new realms here on the Climate Show. Thanks very much, Gareth.
Thanks, Glenn. See you soon.
See ya. Bye.
What good is a drop in the ocean?